So what we're looking at in this particular section is section 1.4, where we're looking at continuity and its properties. Well, I started the lesson really with just asking you, what does the word continuous mean in our everyday lives? When someone has a case of continuous verbal diarrhea, what are we talking about? It means that it never stops, that it's going on and on and on. And continuity means a similar thing, even in the context of a function. Basically, a function that is continuous is one that is completely connected. And if we were drawing it with a pencil, we could put our pencil down and draw the whole function without having to pick up our pencil at all. Another way of thinking of it goes back to what we talked about when we were talking about limits, when we talked about how a limit is all about the journey of getting somewhere. Well, continuity includes the destination as well as the journey. Okay, it's the combination of the two. So taking a look at this, just before we get into the more mathematical definitions of continuity, just go with your intuition. Is this function continuous? Why or why not? Well, if you imagine trying to draw this with a pencil, you would get to that spot where it is at -3, and you'd realize, oh, I got to pick up the pencil and move it to include the dot, then get back onto the function again. So this is definitely not a continuous function. So let's go with some definitions then. If someone is asking you, is something continuous at a certain point? What you're looking at that point to make sure that it is continuous is that the limit that's approaching from both sides is the same as what the actual function is equal to at that point. So all three things have to line up, have to be exactly the same to be able to say that a point is continuous. On an open interval, so we're not so worried about what is happening on the endpoints or whether they're equal or not, but a function is continuous on the open interval AB if and only if it's continuous on every point. So every point, the limit that's coming in actually has this continuity definition. And lastly, a closed interval. A function is continuous on a closed interval if and only if it's continuous on every point in the open interval. And then this one's kind of fun to think about. You've got to imagine it. So if you're looking at f of a, that's where the interval is beginning. The function or the limit that's coming in from the right-hand side has to equal f of a. Makes sense. And then think about f of b, the last point that you have. The function that is coming in from the left of that function, the limit, has to equal what the function is equal to at that spot. Okay, so once again, limits are about getting somewhere. It's the journey and whether you're getting towards a journey, whereas continuity means that the point when we get there is also part of the picture as well. And we can draw a function. If we can draw it without picking up our pencil, it's considered continuous. We've already looked at this one, so let's just bypass it. Let's take a look at this one. Is it continuous? As we look all through the function and specifically at the spot that they've kind of highlighted, at -2, it's definitely continuous at that spot because the limits are equal to f of -2. Is the following function continuous? Why or why not? So we take a look at it and we can see that there is this jump in the function. The function, the limit coming in from the left and the limit coming in from the right are not at all in the same spot. So no, this function is not continuous. And you'll see that I'm giving you a sort of technical definition showing you that the limit of -1 coming in from the left is not the same as the limit of -1 coming in from the right. All right, so in this one, let's identify the intervals on which the function is continuous. Well, it's a piecewise function. It's in pieces. So I can identify pieces of it that are continuous. Certainly the whole function is not continuous, without question. But there are pieces. I can go from -6 to -4, and that's with hard brackets. I can do from -4 to -2 with soft brackets, but then I run into a hole, so I got to leave it. And then I can go from -2 to 0, once again running into a hole. And then I go from 0 to 1, but you'll notice it's a hard bracket on the 1. And lastly, from 1 to 4, soft bracket on 1 and a hard bracket on 4. So there are pieces of continuity in this function. Now here's where it gets more interesting, where we give you the functions in algebraic form and ask you to figure out just by looking at them whether they're continuous or not. Now, looking at this one, you can definitely tell it's a piecewise defined function. So it's coming in pieces. So we need to look at the places. If we look at these parts of the function, the x, the 2, the 2x minus 1, we realize that each one of those on their own would be a continuous function. That's not a problem. But it's going to be about where they meet each other. Do they actually form a continuous function at that spot? Well, if you take a look at the limit as x approaches 1 from the left, so for x, and in fact, I think what I'll do is just go to the next page so you can see it. If I look at the limit as x approaches 1 from the left of f of x, I realize that it's a plain old 1. And then if I jump down and take a look at what it is as x approaches 1 from the right-hand side, once again, the limit will be a 1. So that's good. Those two are going to meet at the same spot. But then when I check what f of 1 actually is, it turns out to be equal to 2, which means that this one is not continuous. And we would say, no, it's not continuous because the limit as x approaches 1 of f of x is not the same as f of 1. All right, let's try this one. Now we did it in class, and I recommended to you that you may need to take some time the first time you look at this, but eventually you should be able to recognize this function and be able to picture it right away. And that will definitely help you. And so if you can draw a quick picture of what it looks like, then you can say, all right, f of x is definitely continuous on the open interval, -3 to 3, and the limits on the left and on the right are equaling what the function is, so everything is a go. This is definitely a continuous function. Then we tried the greatest integer function, and once again, you're going to need to know this function so that you can imagine it in your mind or draw a quick sketch of it so that you can answer the question, is it continuous on -1 to 1? And you can see right at 0 that there's a jump in the functions. So this one is definitely not continuous. In fact, we would say it's discontinuous. You'll notice I'm starting to use that language. And if you had to give a reason, what you're showing then, you find the limit as x approaches 0 from the left and from the right, and you show that they're different numbers. And then you state, because they're different numbers, then this function is discontinuous. One more function, and this one again is one that you need to be able to recognize quickly. The absolute value of a number divided by the same number. Well, clearly we're going to always get something that's like a 1, except when it is a negative number, because when it's a negative number, this guy's going to turn into a positive, and this one's going to stay negative. So for the negatives, it's going to be -1, and for the positives, it's going to be 1. So it creates this really cool function that looks like this. Is it continuous? Definitely not. It's got a jump right here at 0. f of x is discontinuous at x equals 0, and you can show that because the limit coming from the left, the limit coming from the right are two different numbers. All right. Now, this is just a FYI for your information. Algebraic combinations and compositions of continuous functions will be continuous. So if you put functions together that by themselves are continuous, when you put them together, they will still be continuous. So whether you're adding them or subtracting them, multiplying them, dividing them, multiplying them by a constant, putting them inside of each other, if the original function is continuous, then the combination of functions will definitely be continuous too. The only thing you have to watch for is when you take two functions that by themselves they're continuous and you make them a rational function, you got to watch for the quotient being a 0. And if that happens, of course, we're going to have either a vertical asymptote, or it's possible, probably a vertical asymptote, but it could also be that there is a hole as well. So watch out for that. Now, a couple of definitions of words that you need to know. First of all, holes, and then displaced points. So if you've got that first example that we had before, which was a function, it had a hole, and then up above it there was this random dot. If you have something like that, we call it a removable discontinuity. Another way of seeing that is if you can take a single point and just simply move it and plug in a hole for the function, then it's called a removable discontinuity. Vertical asymptotes are often labeled infinite discontinuities. And the other word that I'm coming across recently too is that when there is a jump, like that one you had with the absolute value of x divided by x, there was a jump in the function. We call it a jump discontinuity. Okay, now with these discontinuities, especially the removable kind, it's possible that they can ask you to remove them algebraically. So that's an interesting exercise to think about what it would take. So we'll start with this one, taking a look at it. First of all, it would be useful to figure out where the discontinuity is in this guy. Where is that hole, so to speak? So we're going to factor it. You'll see, okay, there's a hole at -3. And the function when I get rid of the hole is simply x minus 3. So two different ways we can rewrite this function. We could rewrite it as a piecewise function. This is more sophisticated, and I like this. You're going to write that the function is the same as the original for everything except -3. But at -3, if you plug that -3 back in here, -3 and -3 gives you -6. So I've got to plug up the hole. And so at -3, it's equal to -6. And then I've got a function that is completely continuous. You could also simply rename the function by the one that it came simplified to be, simply x minus 3, and that will give it to you as well. This one is nicer because it really demonstrates that you understand there was a hole and you're plugging it. Okay, here's sort of a culminating question. Take a look at, is this function continuous or not? So we can see that it's each one of these by themselves would definitely be continuous, but we've got to check what happens at 2. And so when we take and put 2 in this one, we have 4 minus 2 divided by 2, it's a 1. And 2 divided by 2 is a 1. So the limit as it's coming in from the left and from the right is 1, but the actual point at f of 2 is 2. So we've got a problem. We definitely have a hole. So is this function continuous? No. It is discontinuous. If not, where are the discontinuities? Well, there's a hole. There's definitely a hole, a spot where we have a problem going on. So x cannot be a 0, for instance. And also at 2, we have this hole happening. There's something going wrong with our function. So if there are any discontinuities, identify them. Well, if x is equal to 2 is a hole, so we call that a removable discontinuity. And x equal to 0 is an asymptote, which we can call an infinite discontinuity. And then lastly, they're asking us to rewrite the function to remove them. Well, if you remove them, you could use the very same piecewise function, except for x equal to 2, you would need to change this to 1, and then you would be fine. Another interesting question that they're likely to give you, where they tell you that they want the function to be continuous, but you have to figure out what some variable actually would have to be equal to. So this is a piecewise function. We can tell that if it were these two polynomials, that it would be continuous. So the problem is where it is a 1. The limit as x approaches 1 from the left of f of x has to equal the limit as x approaches 1 from the right of f of x. And so let's go ahead and pull this in. From the left, it would be this function, and we're going to plug in the 1. So 3 times 1 cubed has to equal a times 1 plus 5. And then we solve it and find that a is a 22. Okay, lastly, but definitely not least, this is a theorem that we have to take a look at. And with the theorems, when it comes to the AP exam, we're going to expect you to know these verbatim. You need to have them memorized. And if we ask you to prove that something is in a certain situation because of the theorem, you're going to have to go back to what you've memorized to be the theorem and quote it. So here it is. It's called the intermediate value theorem. So if a function is continuous on a closed interval, a and b, and you should keep in mind what that definition means. Of course, we've already defined that. The limits are the same. The function doesn't have any jumps, so it's continuous on a to b. And the two endpoints, f of a and f of b, their values are not the same, so they've changed. All right, one's smaller than the other in some way or another. And then that we're looking for that k is some kind of a value in between f of a and f of b. What we know is that there has to be a number c, that in that a and b, in the domain a and b, where f of c is equal to k. Now, in other words, this one means that a function has to go through every number in between. Every y has to have an x. It's kind of like saying someone was driving a car and they were going at 20 kilometers an hour, and eventually they got to 100 kilometers an hour. Well, we know that to go from 20 to 100, they have to go through every number in between. They have to go from 20 to 21 to 25. They have to go all the way to 100. Now, it doesn't mean that they don't drop down and go a little bit, whatever. They are going to go every number in between. So the way we use it is the following. Use the intermediate value theorem to explain that the function has a 0 in the given interval. All right, so what we're going to do, you have to make sure that first of all you actually quote that this guy is continuous. So you say f of x is continuous on the closed interval 0 to 1 because f of x is a polynomial. We know it's continuous. And then we're going to check the endpoints. F of 0, when I plug in 0, turns out to be negative 1. And f of 1, when I plug it in, turns out to be 3. So if I'm looking for a 0, in other words, that f of a number gives me a 0, well, first of all, sorry, let me make sure. I'm showing that f of 0 is not the same as f of 1. Okay, the number has changed. Those values have changed. So f of k, and I'm just introducing a random variable called k, equal to 0, has to be in between because somewhere this one went from negative 3 to 3 on the y-axis, so we had to have gone through a 0 somewhere. So here comes the final culminating sentence. Therefore, by the intermediate value theorem, there exists at least one value k where f of k is equal to 0 between 0 and 1. I should have put a k in there. Don't know why it's empty. I think I must have whited something out and meant to go back to fill it in. Here's a sample AP question that you might want to try just to check it out. You'll notice that f be the function above where c is a constant, for what value of c, if any, is f continuous at x equals 2. So the limits coming in from the left and the limits coming in from the right are going to have to be the same. So just like we did in an earlier question, let's set that up. And remember that we're going to be plugging in 2 for our x's. So 2 squared sine 2 pi. It's got to be equal to 2 squared plus 2c minus 18. And you do have to stop and consider, okay, what is sine equal to at 2 pi? So picture your function. You should know it well by now. It's a 0. And so that means this side becomes a 0. On the other side, you have 2c minus 14. Move it over. Turns out c is looking like 7. Okay, there you have it, continuity and its properties. Good luck with your homework, and of course, let me know if you have any questions at all.